Caving. Here is a beautiful cave. It looks like something else. Anyway, never mind. Moving on. Pete and Manaya have decided to climb down a rope into a cave. Okay, so maybe a cave's more like a vertical cave, and then here's the rope. There we go. That's much better. Anyway, that looks like a soda. Anyway. All right, so they're climbing down into this cave, and their equipment, or Pete and his equipment, have a mass of 80 kgs. What is the weight of Pete and his climbing equipment? So weight versus mass, right? So weight is equal to the mass of an object multiplied by the strength of gravity. So our weight changes depending on what planet we're on, or if we're in space, right? Or if we're falling, we feel weightless, for example. So the weight is equal to the mass times g. And we're assuming Pete is on Earth. His mass with his equipment is 80 kgs. Since he's assumed to be on Earth, gravitational constant g is 10. Or more accurately, but it's more close to 9.81. However, in level 1 physics, we can use 10. That's fine. To give us 800 newtons. All right, newtons measuring the force, and weight is a weight force. All right. So that is acting downwards. So if Pete was hanging for dear life on this rope, the weight force is vertically downwards or towards the center of mass of the Earth. Now, using Pete as an example, what is the difference between mass and weight? So mass is the amount of matter in an object. Not saying Pete's an object, but like in a thing, in an object, in a person. It's a very physics word. But then using Pete as the example. So, example, Pete is 80 kgs. So mass is the amount of matter in an object. Actually, we could add measured in kgs. Right? So that's being specific what the units are, a brief definition, and then the example is that Pete is 80 kgs. Whereas weight is the force exerted on a mass. So it's linking it to the mass. Measured in newtons. For example, Pete has a weight of 800 newtons, as we've just calculated in part 1. So to summarize this part 2, to explain the difference between mass and weight, we gave brief definitions. So mass is the amount of matter in an object. We've said what the units are, measured in kgs. And in this context, we just linked it back to Pete. So wherever possible, link it back to the context. However, sometimes that might not be possible. For example, if it was the first question and we didn't have Pete as our context, we would just give this first line. All right, question B. When Manaya is 100 meters from the bottom of the cave, she drops her torch. That's a heavy torch. Calculate the gravitational potential energy the torch has right before it drops out of her bag, right? 100 meters above the ground. So gravitational potential energy, if you forget the formula, it's at the top on the first page. So the potential energy is equal to mass of the object times gravitational constant times acceleration due to gravity rather, and then times height. And now this height is just a relative thing. So in this case, our height would be 100 meters because we're interested in from the bottom of the cave. However, in other contexts, you might have dropped it from, 10 meters above ground level, and you're interested in it falling into the cave, so it would be 110 meters. But here we go. We have height, 100 meters above the ground. G, we already know what G is, 9.81 or 10. And M is the mass of the object. So to calculate the gravitational potential energy, it will be equal to the mass, which is 1 kg, times G, 10, times H, 100. Which equals, what's that, 10 times 100, so that's 1,000. And the units for potential energy, or energy in general, is joules. So that torch has quite a bit of potential energy. I wouldn't want to be 100 meters below Manaya when she drops that. Now, what type of energy does the torch gain as it falls? Okay, so we have our beautiful torch, 1 kg torch. It's 100 meters from the bottom of the cave, falls out of her backpack, and it starts to fall, right? So it's losing potential energy because its height is getting lower and lower relative to the ground, well, the ground of the cave. But as it falls, it gains kinetic energy, right? It gains speed. So the torch gains kinetic energy. While it's losing potential energy. Now, I guess technically it would also gain heat, or rather, it would be losing heat, wouldn't it? Yeah, so let's stick to that. It gains kinetic energy. So it starts gravitational potential, converts to kinetic energy. Part 3, calculate the maximum speed at which her torch will hit the ground, ignoring air resistance. So we can ignore the fact that actually it is losing some energy to heat, right? It's transferring energy out as heat, which then isn't converted to kinetic energy. So we'd say the kinetic energy it gains is equal to the gravitational potential energy it started with, which we calculated as 1,000 joules. And we can say this as air resistance is ignored. If we couldn't ignore air resistance, this statement is incorrect. Okay, and now we're looking for the maximum speed. So the equation for kinetic energy, which we're given, is half times mass times speed squared. So that's the speed we're looking for right here. And it'll be maximum speed right as it hits the ground. So after it's lost all of its gravitational potential energy. Ooh. And we know, just from the statement above, come on, give me a pen, please, that the kinetic energy will equal 1,000 joules. So now we need to rearrange and solve for speed. You can use a formula triangle for this. However, I'm going to do it the algebraic way, which is, in my opinion, far superior. So we're trying to solve for v. So we'll multiply both sides by 2. And I did that to eliminate the half on the left-hand side. Right? Now I want v, not mv squared. So I'm going to divide both sides by m. And then I want v and not v squared, so I'm going to square root both sides. And of course, we have found out we know what m is, right? It's the mass of the torch, which is 1 kg. So I'm just going to replace or substitute in 1 for m. And so the speed is the square root of 2000. Right, square root of 2000. Which as a decimal is about 44.7 units for speed, meters per second. So that's very fast. A 1 kg torch. Bonk on your head. That's why you wear helmets when you go caving. Awesome. Now to get out of the cave, right, they need to climb up the rope. We're given Pete and Mania's mass and how long it takes for them to get out of the cave. And part 1 is to calculate the work done. So a reminder, work done is equal to the force times, or the force in the direction of the distance traveled. So in this case, they have the rope. I don't know how to draw a stick person climbing a rope. That looks like a cat. Anyway, their weight force is acting down. So they're overcoming that weight force by going up the rope a certain distance. So in this case, the work done is the weight force, not W for weight force, but W for work, not F for force, but F for weight force, and then D is the distance, in this case 170 meters. All right, I know a little bit confusing with all the W's, but let's break that down again. So Pete has a mass of 80 kgs, so he has a weight force of 800 newtons. Mania has a mass of 75 kgs, so a weight force of 750 newtons. Now let's do Pete first. So for Pete, his work done is equal to the force, which is 800 newtons, times the distance traveled, which for both of them is 170 meters. So if we compute that, we get 136,000. Then units for work is joules, because it's the energy transferred. So that's how much energy was transferred in Pete climbing 170 meters, overcoming his weight force of 800 newtons. Now for Mania, she's a bit lighter with her equipment, 750 newtons of force multiplied by the same distance to give 127,500 joules. So we've calculated the work done by both Pete and Mania. Slightly different, right? But same calculation. Part 2, calculate the power output. So a reminder, power is work done or energy transferred over time. P for power, not for pressure in this case. So we've already worked out the work done. So we can now incorporate this information, right? The time it took them. So for Pete, power is equal to the work done, which is 136,000, divided by how long it took him, which was 2,200 seconds, to give a power output of 61.8. And then the units for power are watts. Whereas for Mania, her power output, same calculation, just slightly different numbers. Her work done over the time it took her, slightly less, which gives her a power output of 63.7 watts. Now, is that completely accurate? No, because we didn't account for all of like the little forces involved in moving muscles around. This is just looking at it from a macro, like a zoomed out perspective, right? Just thinking of them as just a block or a blob with only one force. In reality, that's not the case, but it is useful information in enough scenarios. Yeah. So now part 3, explain who does more work and also who uses more power. Okay. So looking at part 1, Pete does a bit more work. All right, and why is that? So they travel the same distance, however, Pete has more mass, which means he has more weight force. So let's start with that. So for work, Pete does more work as they traveled the same distance. In this case, it was 170 meters. However, Pete, come on, erase. Pete has a larger mass and therefore weight force than Manaya. Right, and since work done is equal to force times distance, if he has a greater weight force, he's done more work. That's for the work done. Now for power, who exerted, or who had a higher power output? So it was actually Manaya. So even though Pete has a greater work done, Manaya exerted a higher power output. And that's because it took her less time, like considerably less time, because even though she had less work, she did it in much less time than Pete, which made her power output greater. So Manaya has higher power output, as what? As she completed or took less time, as, let's get the wording right. Yeah, as she does her work, which is just the energy transfer, in much less time. Than Pete. So we could elaborate on that last point a bit more, just saying that her work done is less. However, we've touched on that in the first part, right? We've compared their power. So we've justified that Manaya has a higher power, has higher power output as she does her work in much less time. All right, speaking of work, I think I'm done. It's time for you to have a quick break and then keep up the good work studying.